All right, so the next speaker is Joshua Sandor. He'll tell us about thermal bootstrap matrix quantum mechanics.
Do we have lights?
Yeah.
Okay, good. So today I want to talk about this recent work with Minjae, Barak, and Shi about thermal bootstrap of matrix, ungauged matrix quantum mechanics. And yeah, I guess I'll give some references during the talk, but it's mainly based on the work of Kruchensky and Anderson from almost 10 years ago. They really initiated the lattice bootstrap program. And then more recently, there was this paper by Hahn, Hartnell, and Khrushchev, where they bootstrapped matrix quantum mechanics with this technology. And then about a year ago, this group at Cambridge, Fawzi, and Saunderson showed how you can add finite temperature to this bootstrap. And we're just applying it to matrix quantum mechanics now. Okay, so the goal here, we want to be able to bootstrap expectation values of operators in matrix quantum mechanics. And in particular, we'll bootstrap these at finite temperature. Why do we want to do this? Well, the first reason, I guess, since we're all here, is confinement. There are various multi-matrix quantum mechanics models that have a confinement-deconfinement transition as you vary the temperature, and you'd like to be able to probe this using the bootstrap. I think for the majority of us, the interest here is for the BFSS matrix model or other holographic matrix models. So here it's some matrix quantum mechanics that's supersymmetric, and it has a gravitational dual, and a kind of standard entropy calculation. Okay, so at finite temperature, the holographic dual has a black hole, and a kind of standard entropy calculation gives, as a function of temperature, a scaling of the free energy. It's a power law scaling, and eventually we'd like to reproduce this from the bootstrap. So as opposed to index calculations, this would be like a microstate counting match on both sides that's sensitive to like the excitations above the ground state energy. Okay, and then finally, just from a technological perspective, this lattice bootstrap program is relatively new, and as we look at more and more examples, we see the limitations of it, we see where it works and where it fails. So yeah, we just want to develop this further. Okay, so most of what I'll say actually is quite general to quantum mechanics. It's a general framework for bootstrapping quantum mechanics, but the example we'll take here is the one matrix quantum mechanics. So we specify the Hamiltonian. So this is just the quartic potential. These p's and x's are n by n traceless Hermitian matrices, and p and x has some appropriate commutation relation. What's up? Oh, sorry. Good. Okay. Yeah, so this action is invariant under an SUN symmetry, where these p's and x's are in the adjoint. And in most of the literature, this is gauged. In this talk, we won't gauge that symmetry. And I'll explain a bit more why. It's really kind of a technological limitation. Okay, I guess one other comment I want to make. When I say bootstrap here, it's not like S-matrix bootstrap or conformal bootstrap, where you're kind of searching in some space to specify a theory. Here, we're really specifying the theory and then bootstrapping observables within that theory. Okay, so we define the expectation value of the operator as trace over the Hilbert space with respect to some operator, like so. And we want to bootstrap these expectation values. So for all of the lattice bootstrap or discrete bootstrap program, there are three main ingredients. The first is just a normalization condition. Expectation value of nothing is just 1 due to normalization of the state. The second is a positivity relation. So for matrix quantum mechanics, it looks like trace of O dagger O is positive. Likewise, the double traces are positive, etc. And we can expand these operators onto some basis set of operators. And this condition being true for any operator formed like this is equivalent to the following matrix being positive semi-definite. So the matrix M is positive semi-definite, where the entries and likewise for the double traces. By positive semi-definite, this means that this matrix has to have all non-negative eigenvalues. Okay. So we can put this into a computer. It's just a big matrix, but so far this matrix doesn't know anything about the theory, anything about the Hamiltonian. And the way we include that is the third ingredient, which are a set of constraint equations. In matrix quantum mechanics, these have two forms. So the first is we're assuming that we're working with a state that's time invariant. And from this, you can prove that the expectation value of the Hamiltonian and any operator is equal to 0. Good. The second constraint just comes from cyclicity of the SUN trace and the commutation relations. And these combined give you this massive list of linear equalities between the various correlators, and you can just solve those. So an example would be trace of xp, expectation value is equal to trace of px plus in squared times the number. And you could also just trace xp as the operator here, and that gives some expression that's like 0 is equal to trace of p squared minus trace of x squared minus Okay, so you see that the n dependence comes in through the cyclicity of the trace, and the commutation relations, the coupling dependence comes in through this equation here. Okay, so we have a big matrix that has to be positive semi-definite. It's infinite size, but we typically truncate on some basis set of operators. So we usually consider expectation values of operators up to some length, and then we consider all the constraint equations that close onto those expectation values. So again, big matrix, you just solve these linear inequalities, plug the solution back into the matrix, and you have this big matrix where the entries are very non-trivially related to each other with coupling dependence and independence through these equations. Okay, so before I talk more about the Bootstrap setup, let me just mention two additional ingredients that you could choose to include if you wanted. The first is we want to study the theory at infinite n. And one of the benefits of this method over Monte Carlo is that we can directly access the infinite n. We don't have to work at finite n up to infinite n, like Monte Carlo. So here, as n goes to infinity, we can, we'll ultimately get double trace expressions showing up from this commutation relation. And as we go to n goes to infinity, we can just impose factorization. This gives us quadratic constraints now, but there's a method for dealing with that I won't have time to discuss, but we can handle that. So we'll be able to bootstrap infinite n. And then finally, I'm not going to do this here, but if you wanted to bootstrap the gauge theory, you could also include the constraint that this expectation or the state is gauge singlet. So trace of the generator of SUN times any operator is 0. Again, you apply this to the long list of operators, and you get a bunch of constraints between the expectation values. Okay, good. Okay, so the Bootstrap program runs as the following. You basically pick an expectation value that you want to study. For instance, the expectation value of the Hamiltonian, and you ask the computer, it's a numerics problem, give me the minimum value or the maximum value of the Hamiltonian such that my matrix M is positive semi-definite, and I satisfy all the constraints. Okay? And so there are two ways you can think about this problem. The first would be you can just calculate the eigenvalues of this matrix if M is sufficiently small, and you can just sample over different values of the expectation value till you find the optimal one. Or you can plug this into a semi-definite program solver, which is just a big optimization package on the computer that's pretty standard. You literally just hand it this matrix of numerical coefficients and your variables, and you say spit out the maximum bounds or minimum bounds on this variable in my matrix. Okay, so you run this as a function of the coupling, expectation value of the Hamiltonian. The computer will spit out a min bound. And so everything above this line will be allowed. Okay, this is good, but why do we not get upper bounds? Well, we don't get upper bounds because we haven't specified the state that we're taking this expectation value with respect to. So it could be an arbitrarily high energy eigenstate. So we interpret the bounds just at this level as being bounds, like minimum bounds on the ground state energy of the theory. So this kind of up to here was done by Hartnell et al. A few years ago. Okay, so the next thing we want to do is include state dependence into the bootstrap. So that should take the form as an additional list of constraints on the variables. The first example is suppose we consider a pure energy eigenstate. Then the additional input to the bootstrap would be that the trace of expectation value of the Hamiltonian times some operator is equal to the energy times expectation value of the operator. So if your spectrum is discrete, like if you're just doing normal, small quantum mechanics, that works, and you can kind of, as you fix energy, run the bootstrap, and as you vary across energy, you'll see islands in the allowed values of the expectation values, and this will allow you to pinpoint what energies are allowed, and you'll get the full spectrum that way. In our case, we're going to do infinite n matrix quantum mechanics. Our spectrum is continuous, and moreover, this is a double trace expression, just factorizes, and it's kind of trivial at infinite n, so we're not going to do that. Instead, we're going to study the thermal matrix. Okay. So the question becomes, how do we input information into the bootstrap that tells us that we are taking thermal expectation values? So this was worked out by Fozzi et al. About a year ago, and it's quite an elegant solution. It turns out that if you take expectation values with respect to this thermal state, it's equivalent to this infinite list of inequalities being satisfied. So I'll just write it here first. So let me define. These are all matrices. So A has entries. B has entries like this. And then C has entries. Okay. So again, the statement is that if this inequality holds for all these matrices, then that specifies that this expectation value is being taken with respect to the thermal state. Okay, so you see if you pull this guy to the left-hand side, this is some big semi-definite matrix. But we're not quite done because we can't just feed this into a normal semi-definite program solver because it's not, well, you have this nonlinearity. So we have to deal with that somehow. And Fozzi et al. Also provided a way of doing that. And I'll kind of sketch how this works now.
So is there any intuition why this inequality appears from a thermal state?
So on the right hand or on the left hand side, this is some relative entropy, and here this is like the time variation. So intuition-wise, I'm not really sure. It's relating some variation in time to some relative entropy. Yeah. I wouldn't say I have a intuitive picture.
It's roughly the same that the free energy is minimized. That in the thermal state, the free energy should be minimized.
Okay.
I mean, the easiest easiest way to get some intuition is take beta to infinity,
Yes.
and then it's really just that if you vary the state a little bit, you have to increase the energy.
Right.
Then if you allow beta to go down a little bit, and it did, okay, you can reduce the energy a little bit, but you must also reduce the entropy significantly.
I would have thought you would need to impose the KMS condition. Is that related to?
Sorry. By saying we're taking with respect to thermal state, that's KMS.
But this is equivalent to the
Yeah,
KMS condition.
Lieb actually approved this in like the 70s or 80s or something. Yeah, this is somehow equivalent.
Okay, good. So, yeah. So let's take this toy example. So I'm fixing tau and I'm just asking what's the minimum value of x such that this is true, and I want to reformulate this as a semi-definite program. Okay, so the first thing I do is I write the log as an integral. And this f is okay, and I'll approximate this integral now. So here our bounds will stay rigorous, as I'll explain, but they are approximate. So this is some quadrature. And we choose this quadrature of this integral such that it lower bounds the logarithm, like that. Okay, so then we can start by rephrasing for each of these fi's, or f of ti's. We can write that as a semi-definite program. So I'll just switch this t to a ti. And suppose we want this to be greater than or equal to some tau I. Okay, well, you can just check that this is equivalent to this matrix. So this matrix being positive semi-definite is exactly equivalent to this condition. You can just compute the determinant or the eigenvalues here and see that. Okay, so each of the elements here we've rewritten as an STP problem, and the STP problem for this full logarithm will just be introducing a bunch of these TIs such that their sum is equal to the original constraint tau. So again, we want to introduce TIs, their sum is equal to tau, and then we want to say find the minimal value of x such that this list for all I is positive semi-definite, and that will spit out a bound on x here.
Is this like a moment problem that looking for a positive measure and relate that to the semi-definite programming?
Sorry, can you say that again?
I mean, is this like you're trying to look for the positive definite measure so that this equality satisfying, and you relate that to the semi-definite program?
Yeah, that's it. Okay, good. So we've solved this problem for the function. It works very similarly for the entire matrix. So here we introduce auxiliary matrices that I'll call Ti, and such that their sum is equal to the right-hand side of our inequality there. Okay, so you can see that so each of these are Hermitian matrices, and they're the same size as the original C matrix that I had over here. So you can see to solve this problem, we have to introduce a lot of extra variables to the STP problem. But at this point, we're kind of done. So there's an equivalent type of block for each of these TIs. We can just include that as like a block diagonal entries in our massive positivity matrix, and we can just run the bootstrap again, saying extremize the expectation value of the Hamiltonian such that our original matrix is positive semi-definite, and all these extra matrices are positive semi-definite. Okay. Okay, so then we get nice bounds. So we can do this for finite n or infinite n. So for instance, for SU2, the lower bounds look like this, and they match the Hamiltonian truncation values to several decimal places there. We didn't push the numerics too high, so the bounds are like this. but we can go up in n, and at infinite n, we push the truncation order a bit higher, or in other words, the size of the positive semi-definite matrix we considered is very large. And in the plots, the upper and lower bounds really sit on top of each other. So we're really pinning down the free energy as a function of temperature in this one matrix quantum mechanics. Okay, so I guess that's kind of the main result. I kind of want to talk a bit before I end about future directions and what's left to do in this thermal bootstrap. So the first will be multi-matrix quantum mechanics. We studied kind of the Yang-Mills quantum, like unengaged Yang-Mills quantum mechanics. Unfortunately, right now our bounds aren't amazing. They're not super tight. The problem is, well, the problem is kind of generic in these discrete bootstrap problems, is that the number of variables proliferates very quickly as you add more and more variables, and so compute times just are longer, the matrices get bigger, and these semi-definite optimization packages just have a limitation on the size of matrices they can handle. So this is kind of a technological issue, but I think Henry will talk more about how they're solving some of these issues in BFSS. Another development that would be really great is to be able to bootstrap one of our n corrections. So we can bootstrap finite n, we can bootstrap infinite n, but we don't have any systematic way of bootstrapping order by order in one of our n. So that would be great, especially for holographic applications. So eventually, you could imagine if you could add time dependence, you'd want to bootstrap the connected correlator in these theories. So you'd need this, you'd need to add time dependence somehow. But that would be the target for more holographic applications. Finally, I'll talk about the gauging. So this shouldn't matter too much for BFS if we just want to match the low temperature expansion. But for other models where you see confinement or something like this, it might be important. Okay, so what's the issue with gauging? Well, in this expression here, these operators that show up have to be like genuine operators in the theory. So in the ungauged theory, we can put in these like matrices with specified indices and break them down into single trace expectation values. If you're bootstrapping the gauged theory, both of these have to be single trace operators. And so this guy is trivial at leading order in n just due to factorization. So okay, we don't really have a constraint at infinite n for the gauged theory. One thing we thought about doing, which I'll just show the example plot for SU2. You can start with the ungauged model and dynamically gauge. So you just add Casimir to the Hamiltonian and project out the singlet sector. Say that projection is controlled by lambda. Then if the true value from truncation, for instance, is here, now we don't have factorization, so you can still run the bootstrap here for SU2. The bounds are down here. Here we're just getting a lower bound, no upper bound. If you start in the ungauged theory, the bounds are tight, but as you dynamically gauge, the lower bound comes down and actually sits very close to the real value. But unfortunately, the upper bound kind of comes down and then it just goes off. So it looks like we're missing some sort of technology or some sort of input to the bootstrap in the case of the gauge theory, but we're not really sure what that is yet. Okay, so I think that's all I had to say for today. I'm looking forward to Henry's talk about BFSS. Thanks.
Questions?
Yeah, I'm just curious about if you have thought about adding functional algorithm for getting the bounds, because you have the log. What that means that, for example, in conformal bootstrap or EFT bootstrap, you can take some functional, like taking derivatives or integrate it against some other function, but guarantee the positivity. Is this?
No, I haven't thought about that.
Okay.
Yeah. Not sure. Yes.
So when you do the gauging, can you access the polyfill loop somehow?
Yeah, I mean, yeah, in our setup, we're all at equal time. I don't know how to add that kind of observable at this moment.
Yeah, it would be important because that basically gives the winding states and
Yeah.
correlators. I just meant to ask, I didn't get from your talk, like, do you see this Casterly-Salas transition that's supposed to happen?
No.
No, like due to the non-singlets.
Okay, I'm not aware, but
Maybe a related question. Can you comment a little bit on the case of negative G?
sure.
Oh, I guess, yeah, you're only doing positive G, right?
Yeah.
Yeah.
Oh,
Yeah, sorry, no transition there.
yeah. So for negative G, we can basically find some critical temperature. Well, so you fix G negative. There is some critical temperature.
That's probably
sorry,
that's
yeah.
probably what I would say.
Yeah. So we basically, you can run the bootstrap and ask for the expectation value of H. The bounds are good, but it doesn't matter because eventually they kind of close off, and you see that the semi-definite program kind of provides a certificate that no thermal state exists above this critical temperature.
It has to have to do with proliferation of adjoints, right? States and adjoint representation. The vortices.
Okay.
No other, cross.
You had this nice approach for dealing with this logarithmic constraint. I just
Yeah.
wonder if you thought about whether that could be used to optimize something like trace for a log row.
Possibly. I don't know. Yeah.
I guess if they get the energy, they could get the entropy by differentiating.
That's true. That's true. Yeah.